we have seen the ring flipping of the cyclohexane chair conformation, that is from one chair conformer to another chair conformer. And when it flips, or when it converts from one chair form to another chair form, it goes through different other conformations. That is, if we have this chair conformation, then it gets converted to half chair form, then to the twist boat, then to the boat, then again to the twist boat form, then to the chair form, and half chair, and then finally to the chair form. So when there is a flipping from this chair form to this chair form, the cyclohexane passes through all these various conformations. Now we did discuss about the energy of these conformations too. A bit of it. We'll discuss much more in detail regarding the energy and also the stability of these various conformations. Now, this was the energy profile diagram we had said will appear when we draw the energies of the various conformations. Okay, we'll see how it's happening. Now, let us take up the chair conformation first. Now, when we had seen that in chair conformation, you have all the we have the 6 carbon atoms over here, and 3 of them are above the plane and 3 of them are below the plane, and then all the CH bonds are fully staggered, and hence there will not be any torsional strain. And also the distance between the adjacent hydrogen atoms is much above the 240 picometer, which is the van der Waal radius. 120 picometer is the van der Waal radius of hydrogen, and when 2 hydrogens are placed together, it will be 240 picometer. And the distance between the adjacent hydrogen atoms in this chair form is above 240 picometers, so there will not be any steric hindrance also, or steric strain also. Also, the bond angle the bond angle in the chair form is almost near to the 109 degree 28 minutes. The bond angle over here is 111 degree 5 minutes, which is almost near to the tetrahedral bond angle. And the slight increase in bond angle flattens the molecule compound and hence conformation, which will minimize the energy of the system. Now that is one reason. These are the few reasons why we have, the chair conformer is more stable. Apart from these reasons, we have other reasons also. Now we'll just try to rotate the three-dimensional, take up the three-dimensional model of the chair form and rotate it. This is the chair form of cyclohexane. This 3D model I have got from the website GeoGebra. Okay, you can click on this website www.geogebra and type conformations of cyclohexane. You will get this model. Now we'll just rotate this model. Now this is the chair form. You just rotate it. What we find is that these 2 carbon atoms have eclipsed. So you can see this, if we number this as 1, 2, 3, 4, 5, 6, you see that 2 and 3, carbon 2 and 3 have eclipsed. Similarly, 5 and 6 have eclipsed, right? Then even 1 and 4, they are also in the eclipsed form. Moreover, if you just observe this closely, if we consider this carbon atom, that is the carbon 1, as a substituent and carbon 4 also as a substituent, this unit appears like a butane unit, right? So you have 4 carbon atoms here, 1, 2, 3, 4. Okay, so that forms butane. Suppose this is considered as the CH3 attached to the butane. This also CH3. So this appears like only this part. You forget about this part. Concentrate on these 4 carbon atoms. So this appears like a butane Gauch unit wherein the two methyl groups are 60 degree apart. The dihedral angle between the two methyl groups are 60 degree apart. Okay. Similarly, if we rotate this again and bring the other groups together, again we find the same conformations, okay, or the same appearance. Alright, see, you can see here, see, these two have eclipsed. Now this appears as a Gauch unit, butane Gauch unit. Okay, so and this looks like the Newman projection. Okay, so this is actually the Newman projection of cyclohexane. Okay, so we can say that there are 6 Gauch units in cyclohexane. Now we have seen that when we take the three-dimensional model, we have the chair form, and when we rotate it, we get this eclipsed form. Okay, and then again when we rotate, you can see here the carbon 1 which we had marked earlier. It's here now. Rotated, the carbon 1 has come here again. So these units, we have the Gauch units over here. 1, 2, 3, 4. These two are the methyl groups of the butane, you can say. Then it will be the one butane Gauch unit is over here, another butane Gauch unit is over here, and we rotate this, we get 6 such butane Gauch units. Now this appears to be the Newman projection of cyclohexane chair conformation, which is drawn like this. Now behind C2 we have C1, and behind C6 we have behind C2 we have C3, and behind C6 we have C5. Okay, so this is the way we write the Newman projection of cyclohexane ring. Okay, chair conformation. And then when we calculate the energy of the Gauch units, butane Gauch units, we find that there are 6 butane Gauch units, and every butane Gauch unit is equated to 0.9 kilocalories per mole. So altogether, totally there will be 5.4 kilocalories per mole of energy will be more, or will be there in cyclohexane when compared to the anti-conformer of butane. Okay, so so much will be the energy of cyclohexane, 5.4 kilocalories per mole. That is chair conformation of cyclohexane, and that is due to the 6 butane Gauch units. Now from the chair conformer, it goes to the, when it flips, it goes to the half chair conformer. Now in the half chair form, we find that the 5 carbon atoms are in one plane, and only 1 carbon atom is out of plane. Now because of this, since all the 5 carbon atoms are in one plane, there will be a lot of eclipsing interaction. Okay, and also there will be angle strain, because these carbon atoms which are in plane, the angle between them will be 120 degree. Okay, so there will be eclipsing interaction, there will be angle strain. Because of the eclipsing interaction, there will be torsional strain and steric strain also. And hence our half chair form will be having high energy, and that is this is the highest energy conformation among all the conformation of cyclohexane. So the reasons are the 5 carbon atoms are in one plane, there are a lot of eclipsing interaction, there will be angle strain, there will be torsional strain and steric strain. Okay, now we'll move on to now we know that after half chair, the conformation takes up the twist boat form. Now before we discuss about twist boat form, we'll take up the boat form. We'll just look at the 3D model of a boat form. This is the boat conformation 3-dimensional model. Okay, again from GeoGebra. This is a bit tilted. You can see here the boat form. These are the flagpole hydrogens. Okay, Now we'll just rotate this. You can see the CH bonds clearly. Now these CH bonds are eclipsed, axial CH bonds are eclipsed. Now when we rotate this boat form, at this point all the CH bonds and the carbon atoms, they're all in the eclipsed form. Okay. Now again you keep the lighter shaded carbon as the reference. Okay, we'll put it as carbon 1. Now when we take at this point, so you can see here a gauge form. Okay, you have 1, 2, 3, 4, a gauge form. Alright, so 1, 2, 3, 4 is a gauge form. I mean, these 4 carbon atoms together make a gauge form. Alright, again we rotate. Okay, we come across another boat form. Now here again we have another gauge form. See, another eclipsed form. Alright, so we can say that 2, 3, 4, 5, 5, 6, 1, 2 forms eclipsed and the rest forms gauge. So in boat conformation, see here we have another gauge form. You can see here this is one methyl group attached to this carbon atom. Okay, so the back carbon atom, this one, these 4 forms the butane unit. Okay, so we can say that in boat conformation there are there are 2 eclipsed butane units and 4 gauge butane units. Okay, 2 eclipsed butane units and 4 gauge butane units. So this is the way we can show the eclipsed Newman projection of our boat conformation. You just imagine this boat has been put upside down. Okay. Now when we draw the boat form, this is what we get. Okay, now you can see the flagpole interaction over here, and the distance between the 2 flagpole hydrogen is only 183 picometer, which is much less than the 240 picometer. So these hydrogens will in fact be overlapping, and hence there will be a steric strain. Okay, and also you can see the equatorial bonds and the axial bonds over here are eclipsed. We have found it. And hence the the boat conformer is almost 6 kilocalories less stable than chair conformer. It has got 6 kilocalories more energy. Okay, we have other reasons also. That is, when we take up the what we call the Newman projection of a boat conformer. Now this we had seen in the animation. The Newman projection appears like this. Okay, so the bonds are all eclipsed. So we have got almost 2 eclipsed conformer or 2 eclipsed bonds. We can say that there are 2 eclipsed butane units and also 4 gauge butane units. Now this is the way we draw the Newman projection of the boat conformation of cyclohexane. Now when we calculate the gauge unit energy or rate associated with the gauge unit, we find that boat conformation has got higher energy. Okay, now there is, as we had said earlier, there will be torsional strain because of this eclipsing units, torsional strain and steric strain, and also the flagpole interaction. Along with these strains, there will be the gauge unit strain also. Now we've said there are 4 butane gauge units, which will make up to almost 3.6 kilocalories per mole. Plus there are 2 butane eclipsed unit that will make up to around approximately 10 kilocalories more per mole. If we consider the energy of 1 butane eclipsed unit to be 5 kilocalories. It is approximately that, between 4 and 5 kilocalories, 6 kilocalories, or we just take it up as 5 average. Okay, so approximately 10 kilocalories per mole of energy is increased due to the 2 butane eclipsed units in boat conformation. So altogether, we will have 10 plus 3.6 kilocalories, 13.6 kilocalories per mole of energy increase because of the butane units, plus 1.4 kilocalories from flag pole interaction. It must be calories, CAL, not CAK, I'm sorry. Okay, from flag pole interaction. So when we put together these two, totally the excess energy on board conformation will be almost 15 kilocalories per mole than the chair conformation. Right now, we go back to the other, we'll take up the twist boat form. Now, when we take up the twist conformer, the conformer appears like this. I don't have a 3D model for this. Okay, now when you look at this conformer, you find that the hydrogen atoms are skewed when compared to the boat form. See, in the boat form, the hydrogen atoms are eclipsed over here, but here they are skewed. So, in twist boat form, there will not be any eclipsing interaction, and also the torsional and steric strain is lowered. Also, in eclipsed form, there will not be any flag pole interaction because these two hydrogens are placed apart. The distance between these two hydrogens are more than 240 picometer. Alright. Also, in twist boat form, the carbon atoms are not in plane. All the carbon atoms are out of plane. But in boat, 4 carbon atoms are in the same plane. So there will be steric strain. That's why the hydrogen atoms over here in both forms are in the eclipse form. But in twist boat form, we won't have that. So overall, when we look at this, in eclipse form, in twist boat form, there will not be the torsion strain, the steric strain, there will not be any torsion strain and steric strain. There will not be any flag pole interaction, but there will be a bit of angle strain introduced because of this twisting. Okay, so we can say that when we compare the energy of twist boat and boat, twist boat form is more stable than boat form, or twist boat form is having lesser energy than the boat form. Alright, so we have the chair conformer, most stable. Then we'll be having the twist boat form, which will be next to the stability, and then only we go for the boat conformer, and then we have the half chair conformer. Alright, now, even though twist boat form is stable than boat form, it is not as stable as the chair conformation because of the angle strain and also a bit of torsion strain. Alright, so when we you can see here the twist boat form is about 5 kilocalories less stable than the chair conformation, or it will be having 5 kilocalories more energy than the chair conformation. Now, when we plot the graph, let's plot the energy profile diagram of the ring flipping. So we have the chair, half chair, twist boat, boat, twist boat again, half chair again, chair again. So how will it appear? Let's plot the graph of conformations against the energy. We have the energy over here, energy axis. Now we have the chair conformation at the minimum or lowest energy state, or most stable. And it passes through half chair, there will be an increase in energy. Because half chair, we have seen that all the 5 carbon atoms are in the same plane. There will be angle strain, torsion strain, steric strain, etc. From the half chair, it goes to twist boat. Twist boat has got lower energy because of the skewed hydrogen. The hydrogens are skewed and there is no interactions, etc. Now, from the twist boat, when it goes to boat form, what happens? There will be again increase in energy because of the flag pole interaction, and also the 4 carbon atoms comes in the same plane. In twist boat, they are all out of plane. isn't it? So when we plot the graph, it'll appear like something like this. Now, when we look at the energy difference, the energy difference between the chair form and the half chair form is around 11 kilocalories per mole approximately. Okay, and the energy difference between the twist boat form and chair form is approximately 5.5 or 5 kilocalories per mole. And energy difference between twist boat and the boat form is only 1.8 kilocalories per mole. And that's why since the energy difference between twist boat and boat form is very less, these two conformations are considered together. Alright, but actually they must be considered separately, because twist boat is of course less in energy than the boat form. Now, when we move further, after the boat form, it goes back to twist boat form again, isn't it? So you get the energy profile like this. From the boat, again, there will be lowering of energy because it takes up the twist boat conformer. Again, it increases, goes to the half chair form, and then finally it comes down to the chair form. Okay, so this is then how it appears, the energy profile diagram, how it appears. Okay, now when we look at when we say which is the exact conformer of cyclohexane, we have the chair conformer and the twist boat conformer. Boat conformation is having higher energy than the twist boat conformation. And we know that by definition, conformer is those structures, or conformer is that structure which occupies the minima in the energy profile diagram. So the minima in the energy profile diagram is occupied by the chair conformer and the twist boat conformer. Now, since the energy difference between the boat and twist boat is approximately 2 or between 1 and 2 kilocalories per mole, people do not consider them separately. But actually, it must be considered separately. Now, if you are a hardcore stereochemist, you will say that twist boat is the conformer of cyclohexane. Twist boat and chair form is the conformers of cyclohexane, rather than saying it as boat and chair. Alright, so this is the stability and energy of the various conformations of cyclohexane, and also how do we have seen how do we come up with the energies of the various conformations, looking into the torsional strain, angle strain, steric strain, and also the butane Gauge units and butane eclipsing units. Okay, please draw these conformations, draw the energy profile diagram, draw the Newman projections, write the Gauge units, and understand the difference between each, and make yourself thorough with this. Thank you for listening.